Welcome and thank you for downloading this TODEF podcast.
Today we'll have two topics in the two consecutive hours. The first will be about the cockpit and how you measure speed and altitude. We already covered some of that during the tutorial. And in the next hour we will talk about propulsion, one of the final forces that we still need to discuss of the four forces at the aircraft. But first I would like to react on a few questions that I got recently to see if we can cover those. One of them is the problems of chapter 7. You saw that that Anderson uses quite a different notation and some different wording here and there, and this confused some of you. So I'll quickly explain the differences. Main is that for tail setting he used a different sign, as you saw in the two solutions. The number that he got and the number that I originally got are because the tail setting of plus 2 degrees in Anderson means 2 degrees down. And in the notation that I use, the angle I normally is positive up. So watch that. Also some questions about the angle of attack and the lift. Anderson uses the absolute angle of attack. And that's very convenient because in this way, when he gives you a point for the lift and the angle of attack, he automatically also gives you the slope of the lift alpha curve. So what is the absolute angle of attack? The absolute angle of attack is nothing else than if we first look at the standard CL, it's a shift in alpha. With a cambered airfoil, I'll dim the light a bit. They promised me it would work again today, yeah. Okay. If you have an airfoil with camber, you normally have a lift curve something like this. That means that when the angle of attack is 0, there's already a lift. So if we then need to describe the lift curve, we get an offset and a steepness, a slope of the curve. And what the absolute angle of attack is basically avoiding that trouble by having 0 lift at 0 absolute angle of attack. So this is the normal angle of attack, alpha CL, and this is at the same position the absolute angle of attack. In this way, when you get a point at the curve and you get the absolute angle of attack and the lift, you automatically have the steepness of the curve. By just dividing the lift curve through the absolute angle of attack, you automatically get your A, your DCL, the alpha. One other thing I got some questions about is the aerodynamic center and the moment in the aerodynamic center. On the one hand, we have a force, which we give a certain arm, and then it matters what is the reference point, while the moment around the aerodynamic center, we just move to the center of gravity as if it doesn't matter. This confused some of you. So I quickly explain this by, I think the best explanation I found that worked with you was by looking at the situation at the wing and understanding basically that the lift force at the wing is the result of the difference between two giant forces. Remember that we saw the air pressure, that's a huge force, and there's only a minimal difference required of a few percent between the top and the bottom side of the wing to get this lift. But if you get those two huge forces on the downside and the upside of the wing, if they differ a bit, they probably also differ a bit in the point where they apply. If you sum all the pressure differences of all the pressures along the surface, you get a huge force. And so imagine that the lift force is a bit to the back. Say it's 4 something, a very high force, but we'll leave the unit out for now. And let's say that at a difference of 1, we have a force down of 3. Just for simplicity's sake, forget about the units, just imagine the larger force up than down, and they apply at a different position. What we basically do when we talk about the moment around the aerodynamic center, we say we decompose this into the situation where we have the pressure, the difference between the force, 1, applying at the last point, and we have 2 forces of 3 in a different position. This is the position where the force of 4 applies. And this is the arm between. And this basically means that we have a moment, a negative moment, of minus 3 Newton meter, if these are newtons or meters. And we have a force up of 1 Newton, all applying at the same position here. So we decompose the two forces into a moment and a force. Well, if you translate a moment which has equal force up and down, which is basically a couple of forces, then if you move to another reference point, you can see that that shift, that translation, is added to your moment both on the plus and on the minus side. And therefore it doesn't matter. And therefore we can just say, okay, apparently we have a sort of rotational force, the moment, and we have the linear force. So that's what we do by moving the moment around the aerodynamic center. Also, it is an aerodynamic moment. It's a result of these pressure differences. That's something you should be aware of. In the tutorials, we discussed 4 problems. 2 of them were group problems. The solutions of those, or your results with the correct solution, is posted on Blackboard already. The solutions to the other problems, 3, 4, and 5, will be posted this weekend. 5 is about the stability and control, and that's basically the real goal of what this derivation that we did was sizing the tail. And problem 5 is about how to size the tail of an Airbus A310. Actual data, there you can see if you calculate the tail area, what the correct answer is. Well, should be resulting in the tail surface that the actual Airbus A310 has, but I'll post that as well. Those were, I think, most of the questions. I've got some questions about registering for the exam. The registration for the exam will be open tomorrow, and you need to register at the latest 2 weeks before the exam. But I would say, why wait? So starting from tomorrow, you can register at the exam. There's a link on the Blackboard where you can find information on how to do this. Okay. One other thing that we skipped last time when we did stability and control, due to lack of time, was also something that's called the load factor. So for this, let's look at the airplane in a steady turn, stationary turn. And there's a bank angle for which we use the symbol phi, normally. There are 2 different phi's again. If you see the sort of capital phi that you see here, then this is the positive. Then this is the positive direction. If you see the small phi, that's from the perspective of the pilot, and then it's positive in the other direction. But it doesn't really matter, because an aircraft is symmetrical. The direction of the asymmetrical angle is not very relevant. But here we see this phi. So what happens when we have a turn? When you make a turn, you first bank the aircraft. You roll the aircraft, you get a bank angle. And then you have to increase the lift to keep it in the air, because the weight keeps pointing downwards, and you have the lift turned with the bank angle. So now L cosine phi should compensate for the weight. And this means you have to increase the lift until you match the weight again. And that's why you have to pull the stick when you make a turn. And then the L sine phi is also the one that will pull you through the turn, will be the centrifugal force, pulls you through the turn. But what you experience when you're in this aircraft is that you will be pushed in your chair, in your seat, because this larger L and the centrifugal force are together, of the centrifugal acceleration actually, together with the gravity acceleration, result in a feeling as if you experience stronger gravity. So that's why we express this in G. When you fly horizontally, you experience 1G, but if you turn, you can experience more G, and this will gradually increase. So how does this increase? Well, that follows easily from this picture. You see that basically L cosine phi has to compensate for the weight. So how long is now the lift factor? It's basically the weight divided by the cosine. Well, the weight is what? Is 1g. So 1 divided by the cosine is the number of times that you experience the normal gravity. So this means that if you have 60 degrees, and the cosine is in half, then your load factor is 2. So you have 2g constantly if you make a turn something like this, like 60 degrees. So this load factor is very important, similar to the equivalent airspeed. And those two factors, the equivalent airspeed and the load factor, are two important factors determining the performance of your airframe, what your airframe can handle. So what is the maximum speed before the forces on the aircraft become too high, and what is the maximum load factor when the forces on the aircraft become too high? Because it's not just the passenger or the pilot who experience the load factor, it's of course also loading the aircraft. So there's a limit to the amount of G's that an airplane can handle, both in positive and negative direction, often different. So that's one way to describe the envelope, the performance envelope of an aircraft, is to indicate which speeds he can cover and which load factors. Okay, so those were, I think, the leftovers from the previous lectures. So let's continue then, if you overcut this, unless there are questions on this. Is this clear? I don't see any questions, so we go on. Let's have a look at the cockpits. Okay, for a long time, cockpits were what we called analog cockpits, analog instruments. You had dials in there, mechanical instruments, which used the pressure changing, the rate of the pressure, static and dynamic pressure, to get all the data, the air data. And they used sometimes analog computers, electronic analog computers, to get the navigation data. So here, you need more people to control an aircraft, because also the engine had to be monitored in a simpler way, so in a similar way with analog instruments. So often there was a mechanic on board in the cockpit, and they were flown with 3 people. Well, people are expensive, so people were always, the airplane manufacturers were always trying to minimize the amount of people that you need for a cockpit, and this resulted in applying more electronics. And today the cockpit looks very different. We have large LCD screens and computers that basically replace the mechanic on board. But if you look closely, you can also see that on these instruments we still draw the old dials that we had in the analog instrument. We're still not using the new technology to its full potential. Any idea why that is? Why don't they draw a beautiful synthetic vision on this display, like where you can see the mountains, and even in the fog you can fly through the mountains? And why would they still draw the old dials as if they are mechanical instruments? Any ideas?
Gives the pilot confidence.
Gives the pilot confidence, perhaps?
Like for new pilots training, they want to make sure they train on old equipment, so when they have newer equipment, they really easily do it.
Yeah, similar answer. Indeed, for pilot training, it's better. Other ideas?
There's electronical malfunction.
Yeah, electronic malfunction. So less complex systems or something. Keep it simple instead of hide the raw data. Other ideas?
I think that's a very good overview.
A good overview. I'm still looking for something else.
They can still read the old manual.
You can still use the old manual, so you don't need to train the pilots again. Now there's one dominant reason which I haven't heard so far.
In a power cut, they still have the old manual things on the side.
They still have the old manual things on the side, yeah. Here you see the old mechanical instruments as standby instruments still. So for confidence or viewing raw data, you could also rely on those. So why then also copy them and draw the same instruments here?
Because they're simpler, so they're more accurate.
Simpler, more accurate. No, you know what the real reason is? Certification. You have to prove, if you change anything, you have to prove that it works. And this is very expensive, takes a lot of time. And if you just would change, for instance, the color of one of these things, you have to go through a whole certification process, because you deviate from what has been certified until then. And this means that if you want to innovate or change something in the aircraft, and especially in complex systems as a cockpit, the easiest way to do it is to make sure that it fits the current certification rules. And that's why we still have this. And what is the why for the certification rules? Then we get into all the kind of answers that we just heard, pilot training, and, well, basically it's the sort of safety culture in aircraft. At some point, we were sort of in a pioneering phase, and after around the 60s, 70s, the industry became mature, and a lot of things sort of were frozen then, which means kept in rules, captivated in rules, and which makes it much more expensive since then to change. And so there's a lot of debate on whether that's good, because the net result is that with this instrument you're looking at a navigation display which has beacons with 3-letter characters, while the people and the passengers in the cabin, they see a real moving map display, and they see Frankfurt, Brussels, Amsterdam, and they can really see where they are. Where the pilots are using the beacons, and they have to trust that information. And it even happened that a crew landed on Brussels instead of Frankfurt, which by coincidence has the same runway direction. And of course it was also an error of air traffic control. But they didn't notice it in the cockpit because they were just putting in the beacons that they heard, put it in, and everything looked right here. And the passengers knew better where the plane was than the pilots did. Because the screen for the passengers doesn't need to be certified, so it can be modernized much quicker. And there you could really see, so the passengers knew they were flying to Brussels, and the pilots only discovered when they broke through the clouds. They didn't have the fuel anymore to climb again and go back to Frankfurt. So he landed and had to make a, well, not very pleasant call to his company, I think. Here what I did today. Here we see the A320, one of the first full glass cockpits. It was an introduction by Airbus, similar to the side stick. That is still a difference. You see that Boeing 747-400 was one of the first full glass cockpits from the start. They still keep the control column, I think up to this day they do. But apart from that, they also have the similar EFIS layout, only minor differences, larger differences in the flight management system which they use. Some elements of this, you see it is indeed a bit more complex. We still have the old circuit breakers here, but they have been moved a bit to the back, and here we have now a control panel where pilots can do everything that the mechanics did in the old days. The autopilot control panel with the display control panel next to it. The 2 primary displays, primary flight display, navigation display, and similarly here. These are the engine monitoring instruments and system monitoring instruments. Here is the computer replacing the navigator. And here we have the throttle section, speed brakes, flaps, and here we get a lot of radios. Why do they have a printer? Because of A-cars, they have a connection, a sort of telegraph-like connection with the company, and they can send them weather updates or mechanical information. Like there is a digital connection between the airplane and the service part of the maintenance part of the airline. So if there's a failure in the airplane, on the ground, in the headquarters, they can see that, and they will sometimes tell the pilots what to do from a distance.
But can we just read it on their digital screens?
They could read that on digital screens, but the A-cars has a very small screen, I think. So they normally, that's one of the things that you, especially if you get weather information, for instance, winds at different altitudes, it's easier to print it out, and then they have it on paper. And nowadays you also some of the paper is being replaced because they still had a lot of paper in this cockpit by the electronic flight bag. And there they have a much more modern interface on which they can get the weather information. And one of the reasons why this is much more modern is that this falls outside the certification because it does not replace any of the current instruments, other instruments. So one of the tricks to circumvent by still drawing the old dials here, then at the electronic flight bag you can put up fancy instruments like moving taxi displays, because pilots often get lost on the ground, especially on Schiphol. You need a special training to be able to taxi on Schiphol. General aviation has flown with analog cockpits much longer, but now you see that they are able to innovate much faster because they tend to say, okay, this is for the certification, so we've got everything in there, and then here we can do what we want. So they use, indeed, for instance, the diamond here. You see now in general aviation aircraft, you see much more modern screens than in the airliners. because they are not dependent on large pilot training program or acceptance by a large industry. So real innovation now might happen for the future in the general aviation faster than in the airliners. Similarly for the military, they also had, they were faster than the airliners. This is the Spitfire cockpit. Well, the old dials, basic T here, layout. And this is the modern cockpit. Hand on throttle on stick, as the concept is called. So the stick and the throttle are covered with little buttons, which you really have to train before you can use them. It should give you all the controls. No handles for flaps or speed brakes elsewhere in the cockpit, because with high G you don't want to move your arm around to the cockpit. The EFIS that they have is a different name. They have basically a display, multifunction display, and at any display they can give any function, though they tend to have some procedures for that. Here are the basic instruments, stand by still. They get smaller and smaller also in military cockpits. I cannot locate them here right now. You also see that in the, until recently, standby instruments were always mechanical, while nowadays standby instruments can be a computer screen as long as they have an independent power supply and are autonomous. Here is basically where the autopilot panel is in a military jet, and the display control panel is also on the side. And here's some mechanical instruments. So you see also the change in 3 steps from the Spitfire to F-16 to the F-35. And these are the speak up-front controllers. So they have a different speak, but it's the same. Main difference is head-up displays, of course, what they used already in the military fighters long before they used it in civil cockpits. There are some civil cockpits now which also have head-up displays, large head-up displays. So it is very important to have a good reference when you have measure something, right? So it is, there are 2 flight rules basically. Visual flight rules where you do everything visually, but as soon as there are a few clouds, you have to refer to instrument flight rules, IFR, for it's a whole different set of rules and procedures. And well, it is important to know where you're going, and also know the accuracy of what you're measuring, right? So here they notice a 10 feet accuracy. So the speed, this is the old speed meter, a drawing, digital drawing basically of how the old speed meter was. You basically see here that the indicated airspeed dominates. Remember what we said about the equivalent or indicated airspeed? That is the default speed in the cockpit. Here, because it's an electronic version, they have a calculation to true airspeed as well included, and Mach number. But these vary with altitude. This because of the air density, and this because of the temperature, basically. The speed of sound varies with the temperature of the atmosphere. On the primary flight display, they have combined speed, altitude, and the artificial horizon, as well as a little compass, all in one instrument. The top line are basically autopilot settings, which you can view there. But so what are we seeing here? Which speed? Because there are many different speeds. But first, let's look at the units. You already saw something during the tutorial. In aircraft, we use the nautical mile, basically because the navigation principles for aircraft were copied from ships. They were the only long travel means before the aircraft. And the nautical mile has a very logical unit for navigation, because it's the same as 1 minute latitude. In the longitude, of course, it differs depending on how far you are from the equator, but at the equator it's also the longitude. But 1 minute, so 1/6 of a degree, is 1 nautical mile. So if we have the circumference of the Earth, which is about 40,000 kilometers, we divide it by 360, then we get 1 degree. If you divide it by 60 again, you get about 1 nautical mile, 1852 meters. The knot is basically the nautical mile per hour, not to be confused with the imperial mile per hour that the UK or US cars use, because that's 1.6 kilometers, and the nautical mile is 1.85 kilometers. So divided by 3,600 seconds, and this is how you get to this factor, 0.51444 meters per second. The Mach number is another way to indicate the speed. Well, the speed of sound is gamma RT. You'll hear more about the gamma later. For air, it's 1.4. It's a constant. Has to do with the thermodynamic properties of the air. And the speed, the true airspeed, divided by the speed of sound, gives you the Mach number. For altitude, we use feet, 0.3048 meters, that should say. And for vertical speed, we use feet per minute. And normal values for that are like 1,000 feet per minute or 1,500 feet per minute, are normal climb speeds. And of course, you can also calculate to meters per second. Yes?
Why indicate the speed in how many times the sound?
Why would you indicate it for the number of feet of sound? Because you, well, for one thing, it's a handy measure for higher speeds. And the other thing that it really has dramatically changes the flow around an aircraft when you go transonic or supersonic. Then the aerodynamics are completely different. So with most aircraft, you need to stay under the speed of sound. So it's mainly important to avoid going beyond a certain Mach number. Also because of the load on the aircraft. So it's the equivalent airspeed doesn't really work anymore. As soon as the shock waves play a role, then you cannot express your maximum speed in equivalent airspeed, but you need also to cover the Mach number. So at some altitude, your maximum speed is determined by your Mach number and not your equivalent airspeed anymore. Well, normally this is the difference between mile per hour. So at the exam, you don't need to know these numbers out of the top of your head. We will give them, but you have to have some feeling for it to judge whether your answers are logical numbers. So how do we measure speed? Well, first of all, oh yeah, forget the wind. That's an important measure.
Why is everything in planes measured in imperial systems?
Why is everything in imperial systems? It's just historical. It doesn't need to be. The Russians don't do it, and also gliders use SI units much more than powered aircraft. So it's purely historical, because gliders came from the east to us apparently, and for the cockpit technology, this came from the west. Is why we use imperial units. One common mistake is, for instance, I also heard this during the tutorial, that for the power is thrust times speed, some had the feeling that you should need the actual speed, the ground speed, the speed relative to the ground. But everything in the air happens relative to the air. You saw this in the ballooning lecture, so one guy trying to control his direction with sort of vanes, which he could turn, horizontal or vertically, and in this way he hoped to steer the balloon. Well, that would never work, because there is no wind when you're in a balloon. You move with the wind. And it's better to look at it that the Earth is moving underneath you, but the movement relative to the air is zero, and that's why this didn't work and would never work. Anyone who has ever flown in a balloon knows that there's no wind. It's very quiet. It's also one of the reasons why you can hear everybody on the ground. So forget about the wind. If we talk about speeds, it's always a speed relative to the air. And otherwise we'll call it ground speed. So we measure the speed relative to the air with the pitot tube. Mr. Sinke covered this in his force lecture already or not? Okay, so you know the idea. The total pressure comes in here, because this is the pressure that includes the speed, the pressure that you feel when you put your hand outside the window. And the atmospheric pressure, environmental pressure, is measured via a static opening, sometimes in the side of the pitot tube, more often on the side of the fuselage. The difference between the two gives only your dynamic pressure. So this is total, this is static. The difference is the dynamic pressure, and this is used to indicate the airspeed. First mechanically, and now digitally with the digital air data computer. The other thing that we do, we also measure the change of the static pressure to get the vertical speed, and we measure the static pressure to get the altitude. Using this relation means we can just directly translate the dynamic pressure to the equivalent airspeed. Of course, the equivalent airspeed is not the same as the indicated airspeed. There is an instrument error, but there are also some aerodynamic effects, which means the compressibility of the air plays a role. So to get to the indicated airspeed, you normally have to go from equivalent to calibrated, and from calibrated to indicated. Here is the instrument error, here is the calibration. But for low Mach numbers and an ideal instrument, we assume they are the same. The altitude difference. The altitude is you measure a pressure, but you do not know what the pressure at sea level is normally. You don't have an instrument to measure that, and this varies during your flight. So that's why normally we assume a standard reference a standard atmosphere, and at sea level we assume the standard level at sea level during our complete flight, and that's because all the aircraft take the same reference level, means that relative to each other we always have the correct altitude or altitude difference. And during the flight that's the main important, but as soon as we get lower, that where there are mountains or we want to land or take off at some point, then you need to know the pressure at sea level before you can tell what your actual altitude is. The radio altimeter only works at the very last second. You cannot use that a few thousand feet. So the only way to do that is to know the reference level, and that is called the QNH setting. So you need to set the QNH, and then everything works for the air data computer. Here we see again the speed calculation. So you have the true airspeed. You can calculate it with the air density to equivalent airspeed, with compressibility to the calibrated airspeed, instrument and position of the pitot tube to the indicated airspeed. And if you want to know what your ground speed is, which is only relevant for navigation, you have to correct for the wind. You add the wind factor to the airspeed. So these are all the different speeds. If you in a formula see the character V for speed, that is normally the true airspeed. If you look at pilot manuals or Wikipedia performance data, it's always the equivalent airspeed when the speed is expressed in words. Okay. So how do they vary? How do the different speeds vary? I'll put a slide on Blackboard after this lecture, but try for yourself, not just use Excel or a little computer program or something, program your calculator. Programmable calculators are allowed during the exam, as I said, but you can, if you just fill out the table, see what the same true airspeed means for the equivalent airspeed and Mach at different altitudes. See how it varies. See that how huge it varies as well. Or the same equivalent airspeed. If you keep your same speed on the meter, what is the effect for the true airspeed or Mach number? And similar, if you have the same Mach number, what does this mean for true airspeed and equivalent airspeed? And why do they always specify the altitude with the Mach number? And here you see the question we just got, why do you use Mach? Now, here are two limits that you should not exceed with the A330, and here are two limits you should not exceed with the A340. So your equivalent speed should never be higher than 330 knots, but you also should make sure that your Mach number is not higher than Mach 0.86. And the relation between the two varies with altitude. So sometimes this is higher than that, and sometimes this is higher than that. Well, like I said, pressure is not the altitude. Your pressure altitude is not your real altitude. QNH is the pressure at sea level that you set. Normally when you listen a running tape with the meteo information called the ATIS, then you hear also the current pressure at sea level, and this you set in your altitude display here. There's a knob here which you can turn, and then you will have 0 when you're on the ground. Then when you take off, at some point, around 4,500 feet, they will say that is the transition altitude. It should be in the same message, you should have the transition altitude, and that's the altitude at which you change to the standard sea level, and then the pilot has to dial in 1013.5 hectopascal pressure as the reference, or 29.92 inch mercury if you have that kind of setting on your instrument. In our airplanes, most of the times the SI units are used here. And also to avoid confusion on which altitude you're talking about, we use the word flight level above the transition level, and we use the term feet below. So if somebody says, I'm at 5,000 feet, you know it's relative to the sea level, and also that the transition altitude is higher than 4,500. So 2,000 feet, 3,000 feet, those are altitudes expressed in feet. But if he says, I'm flight level 4,500, that is not automatically the same as the altitude, because that is relative to the standard sea pressure. So flight level 85 means 8,500 feet above 1013.5 hectopascal. One flight level is 100 feet. And this is where the altitude is, and here you can also see that he is still, he's using 994 hectopascal, 370. He is at flight level 370 here, and he has set the standard air pressure as the reference, which means that he's using flight level at this time, and this is the actual pressure. Here is the Mach number, by the way, 0.85, above the speed scale. Actually, this is the autopilot Mach number. This is the real Mach number. Of course, the sea level, or the actual altitude, also varies with the altitude of the terrain. We are not really used to this in the Netherlands. In fact, some airplanes are not used to our altitudes, because the first time that the A320, which is the glass cockpit, landed on Schiphol, all the computers crashed because they did not foresee a negative altitude. But of course, there is a different altitude depending on the altitude of the terrain. And there are a whole different sets of wordings for that. You have the QNH, which is the sea level pressure, gives you the actual altitude with regard to sea level. And this is what we normally use. Of course, in our country, it doesn't really matter whether you use sea level or the airport, because they are about the same. But otherwise, you have to use the other setting, the real setting relative to the airport. It's not indicated your QFE, which is basically the pressure at the airport altitude. And this is what you use, for instance, when you land at Mexico City, which is quite high. And all your performance changes as well, by the way. And here we see, for instance, some table that's being used for a certain pressure. They define a different transition altitude to make sure everything works. So they also change the transition altitude. It's part of the weather information. So that is what I have to say about cockpits and systems. I'll focus it mainly today on altitude and speed. Originally we had a 2-hour lecture on cockpits, but in the interest of time, basically giving you more time for the other topics, we scrapped everything except for altitude and speed measurements and the general discussion about the cockpits that we just had. Are there any questions at this moment? Probably what are you going to ask on the exam about cockpits? That will therefore also mainly be focused on altitude and speed measurements. So understand those well, the relation between Mach, indicated airspeed, true airspeed, ground speed, how you go from one to the other, and the different types of altitudes that we have. So know that when we say an aircraft flies at flight level 45, this means you can use the standard atmosphere. You don't need to worry about what any atmosphere is, but if we use a different altitude, then you should look in the problem whether the standard atmosphere is given or not, or whether a deviation from the standard atmosphere is given. Because you've calculated in the tutorial, you've calculated the standard atmosphere. But you can also say, we have today a standard atmosphere, but the temperature at sea level is 5 degrees higher, and all the temperatures are 5 degrees higher. And then you need to be able to calculate also the different altitudes and pressures. You do not need to know the different layers, the base values. We will give a table of those if we go outside the troposphere. And also one of the things I noticed during the tutorial is that some of you use the table in the back of the book. That doesn't work. That's the 59 atmosphere, the 1959 Anderson atmosphere. So you should not use the table. I would say make your own table with an Excel sheet. Good practice to check the formula. Make an Excel sheet that calculates all the different layers, and you have something that you can use for the remainder of your study here. I've also got one, but I'm not going to post them. I think it's better if you try to make it yourself. Okay, let's take the break now, because then we can start with propulsion in the second hour. But we also start 5 minutes before 1:45 then. Okay? This is the Dutch page, but it says from 7 till 12. This is from Sunday to Saturday. So the Friday, I think, is November 11, right? November 11 in the morning from 9 o'clock till, what does it say? 12 o'clock. It's from 9 to 12. So 3 hours. And to get a feeling for the amount of problems, we have about 5 problems often at the exam. There are a few old exams you can watch on Blackboard. But 5 problems, 1 theory, 4 calculation. And to get a feeling of the size, the Mustang exercise that you did, the problem 2 and 3 together are nearly 1 complete exam question. So 1 additional question. And that times 4 is what you have to do within 3 hours. So really have to be proficient at making the problems. There is some time to think, but not about all 4 problems. But some of them you really have to know when you see the exercise, oh, I have to do this, I have to do this. The main problem is with doing exams, there are basically two things you need to know. You need to know your theory, and you need to know how to make exam questions. And that you can only do by doing the homework and the tutorials. Okay, in the morning, November 11th. This hour is going to be about propulsion, about the engines. And if you're lucky, you might even have seen the interior of an engine during the flight. Like this. This is an actual picture a passenger made. But most of us don't have the luck to see the interior of the engine during flight, so we will look at it a bit closer. This is the full picture. Okay. We do not use Anderson's chapter 9, and also with 7, for instance, you saw huge differences in notation. Leading are the slides and the handout. So in the exam, we will use the notation in the handout and also the stuff covered in the handouts for the module A-B. For the aerodynamics module, the next module, they will follow the chapters 4 and 5 much more closely. Because Anderson's is, by origin, is an aerodynamics book. It's been updated to include a bit more, but by origin it's an aerodynamics book. So the propulsion perspective. I told you there are many different perspectives to view an aircraft, and one of them is the power plant group. And like I said, this aircraft actually exists. It's the GB model Sportster. It's made for those races that around two poles, which they did in the States, sometimes still do. And here, really, power is apparently important. Sacrificing many flying qualities. This is an extremely dangerous aircraft. Imagine what happens when you stall with an aircraft like this. Weight will determine how you go down more than the shape of the aircraft. The Wright Flyer is a nice example of the sort of approach that pioneers can take to make real breakthroughs in innovation. When they wanted an engine for their Wright Flyer, they draw up the specs from their calculations, what they needed in terms of power, and also what was allowed in terms of weight. And then they sent letters to all the engine manufacturers asking for this kind of engine with, what is it, 12 to 20 horsepower, the numbers vary that we say, and it should not weigh more than 200 pounds with the fuel included. And all the engine manufacturers send a reply saying, no, we don't have it and we don't think it's possible either. So I think many people in those days would have given up there and start working on beautiful gliders or something. But not the Wright brothers. Then they said, oh, if they can't make it, then we have to do it ourselves. And that's the sort of kind of approach that you take as an engineer. I sometimes also say that's the difference between engineers and scientists, right? Scientists want to know how something works, why something is as it is, while engineers want to know, would it be possible to do this or that? And then they start working. And if somebody says it is not possible, that's of course the best challenge we can get. So that's how they challenged the Wright brothers to invent this engine. There is a replica, I don't know if it's an actual one still available, but we are not fully sure about the amount of power their version could deliver. The historical record says something different than our calculations. So we have to know what it is. But this is quite an important breakthrough. So again, it was not just the aerodynamics, not just the stability and control, but this was also something that the Wright brothers did as the first. Another impression of how innovation can sometimes be blocked by conventions. Imagine that you are considering, like people were at some point, using turbines, like we use in gas turbines, for airplane. Well, in those days, and this was in 1940, mind you, not too long before the actual jets arrived, the US National Academy of Sciences and their committee, the gas turbine committee, so by far the most knowledgeable people on gas turbines, could assure everybody that even considering all the improvements possible, the gas turbine could hardly be considered a feasible application to airplanes, mainly because of the difficulty with the stringent weight requirements. Again, the same reaction. The people who know their stuff, who really know the details, say it's impossible. They're simply too heavy, gas turbines, to be used on aircraft. And of course, most aircraft that we see today for higher speeds or longer distances use gas turbines. And today, we hear again the same for electrical propulsion. Anyone who has a lot of knowledge about propulsion for aircraft or engines, and you'll say, look, the planes are becoming, or the trains are electric since a long time, cars are becoming electrical, we can make electrical boats. In the future, sustainable energy sources will probably use electricity as a medium to move energy. So will we be able to have electrical propulsion in the future? And the answer is standard no. It's too heavy. Both the engines are too heavy, as well as the storage of energy in batteries, for instance. Yeah, so it might be there in 10 years, yeah. Well, there's a sort of Moore's law. You know Moore's law for CPUs, the one that shows an exponential increase in computation power. Currently, you see the same kind of law for battery weight and volume. The amount of energy you can store in batteries is also currently going up very fast. So this could indeed counter this remark. Okay, some theory. So we have 4 different forces at the aircraft: the lift, the drag, and the weight. And today we're talking about the thrust force. The V0 is our true airspeed. Why do we call this V0? Well, from an engine perspective, this is the speed with which the air started when it comes in the engine, into the propeller or into the jet. So aerodynamic people sometimes call it V infinite, so infinitely far away from my flow. The engine people call it V0 because it's the starting speed of the air when it goes through the engine. Because the engine is, of course, a reaction engine. It's similar to rocket propulsion. You push air faster behind you than in front of you, and that is how we generate the propulsion. The boats use, of course, the similar principle with the propeller underwater, but a really different scale because water is 1,000 times as dense as air. Also, the Wright brothers had to invent this, that they started off with small propellers like boats, and then they gradually found out you need larger ones, and how do you need to shape them? But it's reaction propulsion. We keep ourselves in the air by pushing air down, we move forward by pushing air back. We don't have anything else. The principle of reaction propulsion can be tested yourself very easily, making a little, using a tire from your bike, and use that to make this little device on you may have done this already in the past, and then you see from the water rocket, you see what is important for propulsion. In this case, it works best when around half of it is filled with air and half of it is filled with water. Why not fill it completely with water or completely with air? Yeah. So imagine if we use only air, what would go wrong then? You wouldn't have anything to set. Well, the air would go out, right? So too little what? Density of water, mass, indeed. So apparently we need a lot of mass coming out. So mass is apparently important. And water has 1,000 times as high mass as air. So we need water. Why not completely water then? Too heavy? No, not really. Space, the pressure builds up. You can't? You can't compress water, right. Key difference between fluid and gases is that fluids can hardly be compressed and gases can easily be compressed. So this is basically your energy storage. This you compress the air, and this is basically your propellant, the thing that gives you mass. So this gives you speed, this gives you mass. And there's somebody, you can even fly with, supposedly. Do you know this movie, this clip? This is, at some point, I think it's Japanese or something, they claimed that you could fly with rockets. And this is the landing site. Safety is always important. The trick is to get all the corks out at the same time, of course. Okay. If you see him flying around and still moving in a straight arc, I think this myth has been busted, by the way. Because if it would have been real, this is fake. He was basically tethered, because you cannot move like that without the tether. I think at some point you can see it. But the Mythbusters tried it. I think they also busted this myth. But the force is huge. In fact, one water rocket can really kill somebody when he's leaning over the water rocket. So if you start playing with it, be careful. But so mass and speed, that's what counts. So we already talked about the speed. At the beginning you have a speed 0, which comes in the engine. And at the end we have the jet speed that comes out of it, which we jettison the speed. Whether it's a propeller or jet, the principle is the same. The amount of mass is also important. So the amount of air mass that we have through our engine. And those together determine the speed of the force, the thrust force that we get. You can look at it from the perspective of momentum. Momentum is mass times speed, so it's the amount of energy, that's the force that can be delivered by a certain mass. And the actual force is what you feel when you change the momentum. We always know Newton's law as mass times acceleration, and that's normally because the mass is constant. But in practice he said the change of momentum, so the change of the product of mass and speed. Well, in this if we translate this to our example tube here, if you will, where the propeller or the engine is located, we can see that the amount of mass per second that goes through times the speed difference gives us the thrust. You can see also that the units fit well. So this is not a mass, but this is the mass per second. That's what the flux, the dot above the letter, indicates. It's the change of mass per second. And in terms of the engine, it's not really the change of mass, but it's the mass flow. So the thrust can be calculated simply the mass flow times the difference in speed. And so if we get a larger speed or a larger mass flow, these are the two ways to increase the thrust. And this is, of course, the conventional way we write Newton's law. So how can we accelerate the air? Well, one way is a propeller, using propeller propulsion. The other one is the jet propulsion. For the propeller propulsion, of course, that's the way how you move the air, but how you drive the propeller can be done in different ways. Here we see, for instance, you can use the human as an engine. Very bad engine, by the way. Not really, can only sustain the power required for a very short time. In fact, we have somebody at our faculty who's now studying here for third year, was the first Dutchman to build a human-powered aircraft which he could only fly in a straight line for a few seconds himself. And he's currently setting up, he's looking, I think, also for team members to set up a second attempt after having studied here for 2 years, because he did this in high school already, or the first year actually when he came here. He's now looking for an improved version. He's going to build one from which he can actually fly turns, human-powered. He studied basically what we study in this course. He did already in the first 3 years of his high school. Electrical engines, of course, they are around. There are already small aircraft which already have electrical propulsion. The question is, can it replace also the high-speed, long-range propulsion? Here we see, for instance, the one that's also solar-powered. In general, the amount of solar energy that the wing area catches is not enough to generate thrust for the airplane, even if you would have 100% effective solar panels. But maybe now I'm making the same mistake as the gas turbine committee by saying that that's not possible. Because the solar impulse, of course, is already doing something similar, but it's also halfway a glider. What's his name again? Jesse van Kuik, the Dutchman, Jesse van Kuik. So that's how you can find him on the mail. If you're a student here at this faculty, Jesse van Kuik. For jet propulsion, we have the air-breathing engine. We're going to look at that later, but we also have, of course, rocket engines, in which you do not accelerate air, but you burn something to create a gas that you accelerate. Propeller, you can also divide in two different ways. You have the normal propeller, but there's also a lot of interest in the counter-rotating propeller. Has some benefits in terms of efficiency, but it also has a drawback. What could be the drawback of counter-rotating props with respect to normal propellers?
It makes no sense.
Yes, noise. You can imagine the amount of turbulence you get when you get two propellers turning in opposite sides. and turbulence is equivalent with the noise that the engine makes. We're going to look later at the pitch of the propeller blade, because in the old days we had one standard pitch, some standard angle at which we had the propeller turn, and there's a twist in it, you can see. But this twist can also be changed again. We can turn the blades. Why would you want to do that? Would control thrust? Yes. Anything you do to propeller controls thrust. But if you look at it more from the point of view from the flow around the propeller, why would you want to change the pitch? Exactly. It is basically, it's a wing with a twist. So if we see what happens when the propeller rotates, it has a certain angular speed, but of course dependent on the radius where you are in the propeller, you have a different airspeed. And just angular speed times the radius gives you the rotational speed. And this of course means that if we would not twist the blade, we might get an angle of attack that is too high and stall the propeller at that point, and it will not generate any lift locally, which we call thrust for the overall engine in the horizontal direction. But basically it is the same as a wing with an airfoil which has to generate a lift, if you will. And if you look at useful force, here are the two forces that we want basically. The lift force is of course the force that is perpendicular to this plane. This is the one that generates the thrust. And the drag we call basically the side force. But in the end it is similar to a wing. The lift and drag, but we call it thrust and side force. Well, it varies per distance, so it means that at this point you need a small twist because you get a higher speed to get the same angle and to make sure that the airfoil is aligned with the flow in the right way. The sort of numbers you get, most airfoils already stall when you go over like 12 degrees or something. So it's really the angle of attack are always small values. So you need to turn with the flow. And the vertical direction is determined by your airspeed. So if you want to do this right, if you have a fixed propeller, that would only work right for one airspeed. And that's why you want to twist the propeller to compensate for airspeed or rotational speed to make sure that the angle stays right. So that's why we have variable pitch. It covers changes in rotational speed and in airspeed, and avoids the problem that a fixed propeller is only optimized for one condition, one ratio of airspeed and propeller speed. So the available power for thrust, you already used this in the tutorial. So I'm going to skip through this rather quickly. The amount of power after the engine and the propeller has done its work, the available power for thrust can be derived from using plain mathematics. The work performed as thrust times the way that was traveled. If you divide this per second, we get the simple relation: available power is thrust times the airspeed. Of course, this is the power that's available for the thrust. It's not the same as the power that is generated by the engine or the power that was available from the engine to begin with. For a propeller, we call the power that comes out of the engine and goes into the propeller, we call the brake shaft power. So if you buy an engine, you can see what the brake power of the engine is. It's specified by the engine manufacturer, and it's up to you to select the right propeller to get a high efficiency, to get a high amount of available power from the brake, from the shaft power. Well, we can fill this in. So T times V is divided by brake power is the propulsive efficiency. There are also ways there's also a propeller diagram available that for each propeller that will give you the efficiency for the propeller, and this will give you this number, which means that if you have, well, of those four, if you have three, you can calculate the fourth. So let's look a bit more at how this power, this brake shaft power, is generated. The principle is all the same. Even a jet engine and a normal piston engine, they have basically the same principle, even though mechanically they are quite different. But they all have 4 stages: intake, compression, work, exhaust. So what's used in aviation in terms of piston engines? The 2-stroke and 4-stroke are used, Wankel engine, and today you see much more diesel engines in small planes than in the past. But the standard engine was, of course, a 4-stroke engine. So how does it really work? Well, here we see the current 2-stroke has been obsolete, like a moped, right? And 4-stroke is very common. Wankel engine, still mentioned because of its high efficiency, often still mentioned as the future, but it has been the future for a long while, so not sure. And diesel engine, here it says expected, but you already see it introduced, the Diamond aircraft. And also on older aircraft, it's sometimes even retrofitted. So how does it work thermodynamically? This is a diagram showing the pressure against volume. And the pressure is, of course, pushing against the moving piston. So if you want to know what the amount of work is being done by the gas inside an engine, we can just basically say that it's the force times the movement of the piston. But the force, of course, is the pressure times the area. So if we assume this as a quasi-static, this is a thermodynamic property we'll forget about now, we can say the amount of work is the force times the displacement of the piston. And this is nothing else than the pressure difference, just the extra pressure we get inside compared to outside, times the area times the movement of the piston. In other words, this means that this area, because this is similarly, it is basically the area times the travel, is the change of volume. So you could also say that it's the pressure times the change of volume. So pressure times change of volume is apparently the amount of work that a gas does. So if we then draw this diagram, pressure against volume, this means that if we do something, if we change the temperature or we change the volume, in this case we have a constant temperature, but we change the volume, the piston is moving, volume gets larger, then the pressure becomes lower. So this is a P times V that's constant because the T is constant. Then this area is basically the amount of work that was being done by the gas here. So if we have a complete cycle where the temperature goes down outside and the temperature goes up again, or the temperature goes up and then it's compressed again, and then we, let's see, here's where the temperature goes up. So here's the burning, then we have a higher pressure, and then we increase the volume again, and then we lower the temperature again. Then we have to compress again, and this is the cycle, the 4 strokes of the engine. Well, if we do this, you can say that this is the amount of work that's being done by the engine at high temperature when it expands, and this is the amount of work that is being done when compressing the air. And the trick is, of course, the temperature difference. So when you expand at a higher temperature than what you compress, then you get a net difference of work, and this means that the area of this PV diagram, this area that's enclosed, is basically the amount of work that the engine performs at 1 stroke. So if you know the strokes per minute, then you can also count the power. This is one cycle, I should say. No, the 4 strokes are in 1 cycle. So we have basically 4 stages. Let's call it stage because otherwise we get confused with the 2-stroke engine. It basically does the same, but at 2 places in a different phase. So we have 4 stages of the Otto cycle. We have the compression, we have the burning, we have the expansion, and we have the cooling. The cooling we don't do ourselves. What we often do is we just throw out the hot air and take in new cold air. But the principle is the same. So you can just calculate basically the integral and then between the upper power curve, pressure curve and the lower to get the work. So here we say, if we compare it with the mechanical properties, we get the compression here. It's hard to see with the green. We get compression here. Here we burn, we get to a higher temperature. Then we get the work done, expanding it. The piston is moved. And then we get the exhaust, bringing us back to the original pressure or original temperature. So this is basically the same principle over and over again. You see this, this is because we do not have the actual, we do not use the same air over and over again, so we get it at a different, we get it from the atmosphere originally. But this area is basically what the amount of work that we get. Throttle control is basically controlling the amount of gas mixture that goes into the engine is how we control the power that's being delivered. There could have been other ways, but we do it that way. So we have a float here, and there are different mechanical implementations for this. A float here, air passes by, takes a bit of the gas with it. It vaporizes here. And this mixture, we control the amount of mixture that goes into the engine. That is what you control when you control the thrust force. Here's some beautiful animation showing the setup, the different setups you have. Inline means they are all the different cylinders are in one line. This is the most common setup. But you also see, for instance, the boxer engine in general aviation aircraft. And there are different ways, for instance, the radial or the V. And they all have different mechanical advantages and weight-saving opportunities. So those are piston engines. But if we look at air-breathing engines, the turbofan is also one that's used. So jet propulsion and propeller propulsion. If you look at jet propulsion, we have 3 different types: turbofan, turbojet, and ramjet. And then we have all, again, different types. Turboprop is basically using a gas turbine and still a propeller. You see a lot of turboprop engines nowadays on airplanes. Do you know why? Why not stick with the piston engine? Yes, it's mechanically a turbine is much easier. It has less moving parts. If you saw the pictures of the piston engines, you saw a lot of mechanical parts. You need to have more friction. Every piston has its friction, the opening, the throttle. It's much more complex, and especially when you go into areas where there's sand or stuff, there's dirt in the air, it's much easier to get problems with your piston engine, and the maintenance on the turbofan is much easier. So that's the main reason why they moved to turboprop engines. And for the jets, of course, it has another advantage, as we will see later. I'll skip that for now. So here are the 4 phases again. It's often sometimes referred to as suck, squeeze, bang, and blow. These are the stages of a jet engine. The intake. Then first we have to compress the air. So we go up the slope, we increase the pressure and reduce the volume. I should leave this out for now, right? First go. Distracts too much, apparently. So we have the compression first. We have a lot of radial fins there which actually compress the air. Before we ignite the fuel in the combustion chamber, we go past another set of radial fins again, the turbine. This is the compressor, combustion chamber, and this is the turbine. And then we get the exhaust. And so what we do here is we take off some energy that we produced in the combustion chamber to drive the compressor. And that's why we have the difference between the upper line and the lower line as the net efficiency. Here we take out the energy of the flow. If you have a turboprop, this is also your main energy generator because you connect a shaft to the propeller. Today we also often see sometimes, oh, there we get it again, okay. Oh yeah, that it's really dangerous to be in front of the engine is also something where I've got a nice video clip about. It's always, are always signs, be careful with the jet blast, and you probably know the clips about cars being blown away by the jet blast, but the intake can also be dangerous. Here we see, I think it's an A6 on the Navy, or is it something? Yeah, I think it's an A6. And you see that this guy is really sucked into the engine. If we see it in slow motion, you can see it better. He gets too close, and then it really has huge power. If you wonder what all the bits are that come out at the back, I don't know, but most of it is engine parts. You see all the bits coming out? All engine parts coming out. The compressor are really like a lot of... Here is him again, after the incident. A few hours later, he survived. Only some head injury and some other injuries, but he really survived, so a lucky guy. He got stuck in the inlet soon enough to avoid being part of the pieces blown out on the back. Okay. Well, the easiest way to do it is, of course, to forget about the compressor and turbine and just take in the air, add the fuel, burn it, and squeeze it out again. And this has indeed been done. This is the ramjet. It was on the V1. Very simple engine. You leave out all the mechanical parts, basically, but of course it needs to be started up, so it already has speed, similar to the jet engine. I think one of you rightly asked, how do you start it? Well, you cannot start it without some external help. So, for instance, indeed, the APU could provide the electricity, but otherwise an external electric generator has to start the turbine before they can actually get it running. Well, with the ramjet, it's even worse. You really need quite some speed to get this going. There was also once a helicopter which used this, a Dutch invention. They used ramjets on the tip of the rotor. And then you don't need any mechanical parts to drive the rotor shaft. You just need to give it fuel and it would work. Well, the amount of fuel you can put in is about the only way you can control it. But these examples, they are indeed difficult to control. This didn't need any control. The guidance for this was very simple. Just point it in the right direction, and the destination was determined by the amount of fuel that you put in. But London was quite a large target, of course, so it would work. It was mainly to scare the population. It didn't mean to hit military targets. And this one had also some drawbacks. Can you imagine the drawbacks of using ramjets on the tip of your helicopter rotor? Sound, yes. Already tips that go through the sound barrier create a lot of it, but this really creates a racket you don't want to know. So they first tested this in the area of Rotterdam, at Zestienhoven, but there were some complaints from the people living there. And so they had to continue the tests elsewhere, and they had to go to the northeast polder, because there no one was living yet in those days. And that's why currently one of the two sites of NLR, our National Aerospace Laboratory, is still in the northeast polder. That's because of this helicopter. Well, this is the real jet engine. Here we see the compressor, a lot of blades that compress the air when the area becomes smaller as well. Here we see the combustion chamber. So the inner side is basically a ramjet. And then we have the turbine via a shaft driving the compressor to get the engines. We first need the energy here before we can start working here. So it needs to rotate. The jet engine is basically a combination of a turbine and a ramjet, if you will, because they have the turbine in front, but then when we use the afterburner, as they call it, you're basically using it as a ramjet by injecting a bit of extra fuel in the exhaust, well, a lot of extra fuel in the exhaust, you get the ramjet effect. Ramjets are not very efficient in terms of fuel, but it's a way to, with the same lightweight engine, to generate extra thrust for a short time during maneuvers. To improve the efficiency, we really need this system, and it even works better if we have an extra shaft for a second stage. For the propeller, we use the one turbine to generate the compressor, but we can add another turbine to get a turboprop. And this is basically the setup of a turboprop engine, or turbo shaft, it's called. It could also be used to drive a helicopter rotor. Most helicopters use a gas turbine to drive it, as you see here. And most aircraft use a turboprop as for passenger propeller. It's still the most efficient way to propel an aircraft at certain speeds. A propeller has an extremely high efficiency compared to engines without a propeller. It's still better. If you can design it right, it's the highest efficiency. We might see, when there's more pressure on emissions and oil price, we might see an increase of turboprops over jets. Here are a number of turboprops. But the same thing you could also use to add a second stage of compressor. And in this way, we create a fan in front, and we can take in much more air. We could use it in different ways. It's not used as an extra fan to compress air, but you can also use it to propel yourself through the air. So this is sort of in between turboprop and jet engine here. It's a turbofan engine, where we use the fan also to propel the air and to get increased thrust. Well, why did we change it? Because this has gradually, the old passenger aircraft had a pure jet engine, and nowadays nearly all aircraft have a turbofan. Well, to know why that is, we have to look at the principle a bit further. One of them, this is the fan can be really large. So the bypass ratio, the amount of air that you take around the engine compared to the amount that goes through, has increased over the past few years. Why is this? Well, here we see the pure jet engine. Here we see a bypass 2 shaft, and here we see a 2 or 3 shaft bypass. So different stages. We have 2 stages internally here, and the third one is actually the turbofan. What you see is that with the jet engine, you have an extremely high amount of speed that you need to give the air. When you have more air, you have more mass flow, you can use lower exhaust speeds to get the same thrust. And it also means that, of course, the noise becomes less. This makes much more noise than this. So in this case, the higher bypass ratio, the bypass ratio is the amount of cold air over the hot air. This is how we call it. It's called the cold flow, and this is the hot flow. And the 2 mass flows, if you divide them, are the bypass ratio. They are, of course, also easy to calculate by just looking at the front area of the center stage and the bypass stage. The front area there, the speed has the same, the air still has the same speed, which means that the ratio of the front area is about the bypass ratio. Well, more air, less velocity, and you get a higher propulsive efficiency because of that. Why is that? Why is also because this is nice for noise, and it's often that we see in aviation that airlines or manufacturers want to show how green they are, so we want to create less emissions and we want to make less noise, and look how green we are. But very often, if you look underneath, there's another reason. If you create less emissions, you use less fuel, and that's of course something every airline wants. And similar here, the noise is really nice, but in fact it was a side effect. The main reason was something else, the propulsive efficiency. Why is that? Yeah, most cost of an airline is fuel, so it's driven by fuel, so it's very important. But why would adding a larger fan create a higher propulsive efficiency? Why not bring everything through the jet and just have this high speed? Well, it's relatively simple. If we look at the 2 things which happen inside an engine, you can again use high school physics to explain this. So what happens with the jets inside an engine? We have to create kinetic energy to accelerate the airflow. This kinetic energy is simply the amount of kinetic energy the exhaust has minus the amount of energy that the air had when it came in the engine. So half the times the mass flow per V jet squared, V0 squared. If we use the mass flow, we get the amount of kinetic energy we put in per second. In other words, the power we have to spend to accelerate the jet. We also know that the thrust that came out is the mass flow times the difference. No squared, no half, just the mass flow times the difference is the thrust force that we get. And we also know that the available power is the thrust force times the speed of the aircraft. So with this, we can calculate the efficiency of a jet by dividing the available power times the power that we had to the energy that we have to use to accelerate the jet. We can come up with a very neat equation. The efficiency of the jet is available power divided by the power that we put in. So this is what we got out, this is what we put in. T times V0, the airspeed, and this is the amount of kinetic energy we had to put in. And then, because Vg squared minus V0 squared, we can also write as, like, A squared minus B squared is the same as A plus B times A minus B, right? So if we write the same formula here in a different way, we can make this equation much simpler by taking out this, by taking out that, and we basically are left with phi0 times half Vj plus phi0. And then if we divide everything by phi0 and we put the 2 on top, we get a very simple formula for the jet efficiency, and we can see that it's 2 divided by 1 plus Vj over phi0. So here we can see what would be the ideal Vj to get 100% efficiency. Because that's what we want, of course. We want 100% efficiency. What would you need to do? How do we make this 1? Yeah, right, this should be 1 as well. So 2 divided by 1 plus 1, then we have 100% efficiency. So if we make Vj equal to Vh0, we're done, right? What is then the net thrust that we have delivered? Also 0. So we can deliver 0 thrust with 100% efficiency. So again, you see the trade-off. You want more thrust, you get some less efficiency, but you can also see that it's always a good idea to keep the jet speed low. If we still want thrust, but we want to keep the jet speed low, so this is fixed. We want to keep this, but we want to lower the jet speed. What do we need to do? So we want to lower this and want to keep this high. What do we need to do then? Lower V0. Well, this is also sort of given. They just want to fly this speed. Okay, so V0 is given. We want to keep this low. We want to keep this high. What can we do? I hear a lot of the same answers now. Indeed, increase the mass flow. The only way to get the same amount of thrust with a high efficiency is to create a lot of mass flow. That's a turbofan. By having this large fan in front of the jet and having a huge bypass ratio, we get a huge mass flow and a lower jet speed. So that's why we get a high jet efficiency for the same thrust with this. And that's why these engines have become bigger and bigger over time. The large diameter is caused by the jet efficiency. And of course, then we say we do this to avoid noise. We do this for the people living around the airport. Oh, by the way, we got a nice high jet efficiency. Well, you can see you can also make some calculations. If we take a V0 and we have a V0 of 250 knots, we can just take this exhaust speeds and see what the jet efficiency is. Just fill it in. And you can see that if we have no bypass with this, that you have a jet efficiency of 30%, and we nearly double it by using a turbofan, which has this much lower jet efficiency. These are simple calculations. You need minimal data to see the effect of this. And this is, of course, huge. If you see the amount of work people spend to get an increase of 1% in efficiency, and just by changing this, we get from 31 to nearly 54%. So that's huge, and that's why the engines are huge. Well, that we get lower noise, of course, is also a good way to sell it. Here you see the effect, the relative noise level in decibel. You see here the different things we did. So from, well, here you see basically the main thing that you see here. Let's forget about all this. The thing is that the noise really goes down enormously. This is a logarithmic scale when you increase the bypass ratio from 0 pure jet engine to the ones that we see here. So that's why the engines are indeed very big today. Here, look at this. Look at the enormous bypass ratio compared to the pure jet part. So one more thing is the amount of engines. In the old days, you could recognize an airplane really easily by the amount of engines and where they were located. And nowadays, we see nearly all new aircraft have 2 engines underneath the wing, except the very large ones, like the A380, they still have 4, and 747, but most of them have 2 engines. In the old days, there was a big advantage of having 4 engines, and the main reason was that this gave you the reliability to cross oceans, to cross the Atlantic or the Pacific. And with a twin engine, this was not allowed in the beginning, because if you would lose one engine, you might not be able to reach land. because you have a lower efficiency when you fly. If you have asymmetric thrust, you get a lot of drag, and even if you have enough thrust, you still waste much more fuel. You probably won't make it to the other side of the ocean. So in the old days, you needed 4 or 3 engines to go to the other side. So you saw the DC-10 and the 747 were basically the transatlantic aircraft. Nowadays, we go across the Atlantic in a 777 or A330, 757, and they all have 2 engines. And that was basically, since we introduced ETOPS. ETOPS are the rules for under which conditions you are allowed to cross the ocean with 2 engines. And that, of course, has to be very reliable. In other words, the engine should be turning or the passengers are swimming, is the sort of joke that they also made for ETOPS. But this is extended twin operations. At some point, they thought the engines didn't just improve by efficiency, but also in reliability, sufficiently to have the rules in place that you could cross the ocean with 2 engines. There are some restrictions here. They change sometimes, so I'm not sure whether these are the latest, but depending on the rules and types, you have to be able that you can still divert. So there is a certain rule about the time that the flight time that you have to be away from the shore, from the land, which also means that there are still some parts that are restricted to 4 engines there, but they're getting smaller all the time. What is the future? Well, air-breathing engines. We see a return of the counter-rotating propellers. The start of that was actually during the 70s, when there was the oil crisis. People were afraid we would get very expensive oil, and that's when they started investigating counter-rotating propellers, because they were extremely efficient. And this all sort of stopped when the immediate need was gone. And now we see a gradual increase of the price of oil, and we also see in the future decades the scarcity of oil. And now there's an increased interest again for this type of engines, and everybody is really sorry for the time that we wasted by not researching them in the past few decades. So they are looking at it again. Of course, there's also recently we saw military hypersonic vehicle. There's still research ongoing for hypersonic vehicles, and they use ramjets, but then a different type of ramjet. In all the aircraft that we have seen so far, the air is compressed but also reduced in speed. All engines that we've seen so far, the speed inside the engine is subsonic, because otherwise we get shock waves and we get all kind of trouble. Similarly for a ramjet, the speed is compressed and reduced in speed for a ramjet, but with a scramjet, we want to keep the subsonic flow in the engine, and scramjet stands for supersonic combustion ramjet. So for high speeds, you can use the scramjet, but clearly not for lower speeds. So the trick is often how to combine getting at the high speed and actually flying at the high speed. Well, a number of key figures to get a bit of a feeling for the different kind of engines we see here. The jet engines, the T650, that's the Fokker 100 engine. General Electric. Even if you buy an aircraft, you often have the option to choose between 2 different engines. So the engine is such a complex part, it's really the most complex system in an airplane. You can select your own engine with the aircraft type. Often you have an option between 1 or 2 engines, the Rolls-Royce versus the General Electric. Currently this is one of the largest engines. The bypass ratio here is 9. So remember that the figure just went to 7. 9 times the amount of air goes around compared to what goes through the jet engine. 8.5 is another one, and the Concorde is even a different, and this is a pure turbojet. Of course it's an older aircraft and you have higher speeds there. Remember that for a high-speed aircraft, you still want your VJ to be higher than V0. So there, the low exhaust speed is not good news. So for higher speed aircraft, and that's also why the military fighters are not flying with turbofans. Okay, I leave it as this. If you want to know more, you can always find more information on mechanical. How Stuff Works is a great site for engineers.
Please visit our OpenCourseware website for more information. See you at our next podcast.